Oops. All right, we're going to do some more Laplace transforms here using a couple of other different operational properties. We're going to do an example each of when we multiply by t to a power, when we do the Laplace transform of a convolution, and when we do the Laplace transform of a periodic function. So for this particular one, let's look at a couple of these problems that are in the end of section 7.4, which starts on page 289. So let's look at, this is number 8, excuse me, no, yeah, let's do number 8. Number 8 on page 289, because this is going to reinforce a couple of the ideas, including one that was on the previous video. So we want the Laplace transform of t e to the negative 3t cosine of 3t. All right, so notice that this e to the negative 3t is another one of those translation ones like we had in the previous section in 7.3. We have this function, t times cosine of 3t, which is multiplied by that e to the negative 3t. So we'll handle that separately. Let's just first go into look at the Laplace transform of t times cosine of 3t. So we have t to a power, and then we have the cosine, or the function multiplied by that t to the power. The theorem that we're going to use here is if we have the Laplace transform of t to the n f of t, that's going to equal negative 1 to the n times the nth order derivative of the Laplace transform of s, or excuse me, the Laplace transform of f of t, where that, again, that n, the n that we're using here is the same as that power of n. So each power of n, or excuse me, each power of t represents one derivative. We have to remember this negative 1 to the n power because it alternates negative, positive, but notice in general we want to take the Laplace transform and differentiate it if we've got it multiplied by a power of t. All right, so let's go back over to this one. We've got t to the first cosine of 3t. So we want to take one derivative, because n is 1, multiply by a negative, and take the Laplace transform of cosine of 3t. So we want a negative of the derivative of Laplace transform of 3t is s over s squared plus 9. And we can use the quotient rule to get at that. It would have s squared plus 9 minus s times 2s all over s squared plus 9 squared. So we've got an s squared and we have an s squared and a minus 2s squared. So I'll have 9 minus s squared on top, but we get a negative in front, so I'll just write it as s squared minus 9 over s squared plus 9 squared. So that would be the Laplace transform that we're looking at in this particular case for just t times cosine of 3t. All right, but notice again, it wasn't just t times cosine of 3t. It was t cosine of 3t times that e to the negative 3. So we've got to do that adjustment, that translation based on that power. So in this case, the Laplace transform for our t e to the minus 3t cosine of 3t would be s plus 3 squared minus 9 over s plus 3 squared plus 9 squared. And that would give us our Laplace transform for that particular function. All right, so that gives us an example of how to use derivatives to help us get Laplace transforms of functions when those functions are multiplied by a power of t. So let's do one where we've got a convolution integral. These are actually pretty nice because you can just do the Laplace transform by multiplying. So let's do a couple of these. Let's look at, let's say, number 28 on page 290. We want the Laplace transform of the integral from 0 to t of sine of tau cosine of t minus tau d tau. Again, the part that's telling you that you've got a convolution integral, you've got the integral from 0 to t, and then you've got kind of this, well, opposite idea, if you will, with the arguments of the functions on the that you're in the integrand. So notice you got a tau, and a t minus tau in there. So those always have to be, you have to have a function of tau and a function of t minus tau to be a convolution integral. All right, once we do that, we know that this is just simply the Laplace transform of sine of t times the Laplace transform of cosine of t. That's our theorem for our convolution integrals. If we have a convolution integral, we can just do the Laplace transform of each piece and multiply. That's actually a nice property. So for this particular one, sine of t is, of course, 1 over s squared plus 1, and cosine of t is s over s squared plus 1. So we just get s over s squared plus 1 squared. So got a nice solution to this particular problem, pretty straightforward. Let's see if we can do another one. Let's look at number 30. It's a little bit more complicated, but not bad, but it uses one of the other ideas that we just talked about above. But with the Laplace transform of the integral from t times the integral from 0 to t of tau e to the minus tau d tau. So right now, this is a convolution integral, but notice that your second function is 1. So if we were just looking for the Laplace transform of the integral, your second function of t minus tau would just be 1. So this would be the Laplace transform of t e to the minus t times the Laplace transform of 1. There's a couple of ways to handle this first Laplace transform. Probably the easiest is this is t and this is translated. So we can do that as 1 over s plus 1 squared. Remember the Laplace transform for t is 1 over s squared, and then you would have your translation to the left by 1 unit. And then of course the Laplace transform of 1 is just s, so we get 1 over s times s plus 1 squared. Notice that that's just the Laplace transform of this part. We now have a t times that. So using that previous theorem, we know that the Laplace transform of t times the integral will be the negative derivative of this Laplace transform we just found, which would be negative of, well, we could do this, let's do this by multiplying out the bottom here. This would be s cubed plus 2s squared plus s. So we would get negative of s cubed plus 2s squared plus s to the negative 2 times a 3s squared plus 4s plus 1. Forgot my plus 1. I apologize. So if we write that pretty as a fraction, we would have 3s squared plus 4s plus 1 over s cubed plus 2s squared plus s squared. So again, we can use these theorems in multiple situations, where in this particular example, notice that we used the translation theorem here for this one, and we used the derivative theorem here for this one, and we used the theorem for Laplace transforms for convolution integrals. So again, we can do this in several steps and get the answers that we need. Let's do one more where we have a Laplace transform for a periodic function. Let's look at number 51 on page 291. I'll let you look up the problem in the book, but just to give you just a quick graph, you've got this particular function where you've got these little sawtooth pieces going on. The first thing that we notice is that this function is periodic, that we've got this piece is repeating itself over and over and over again, and the period is b. We can figure out that particular function because it's pretty easy, actually. It's a line, and it's got a slope of a over b. So this must be just y equals a over b t. pretty straightforward. So when we do the Laplace transform of this particular function, remember, according to the theorem, that's 1 minus e to the negative sb, the period, integral from 0 to b of the function that we came up, the formula for the function we came up with, a over bt, and that's times, of course, e to the minus st dt. This, again, is the integrand for the general integrand for the Laplace transform. It's just going from 0 to b rather than from 0 to infinity. If we use GeoGebra to help us do that particular integral, because I don't feel like doing it by hand in this particular case, let's get the spreadsheet up. Not the spreadsheet, sorry, the CIS up. We want to do the integral of, let's do e to the negative st times a over b times t. Let's put in some multiplication signs just in case GeoGebra has any issues. And we want to do that with respect to t, and we want to go from 0 to b. There's our Laplace transform, ab e to the minus st over 2. So we can write that in over here. So we would have 1 over 1 minus e to the minus sb times ab e to the minus sb over 2. So that would be our Laplace transform for that particular function in this case. Again, using the theorem here for our finding Laplace transforms for periodic functions. And that's just another example of being able to do Laplace transforms.